Other than that, how are we doing today? Doing okay? We're migrating over here. Is everything all right? Okay. Just- Okay. So we're going to continue in chapter 14, and we are going to talk about the chain rule, which is the kind of most important expansion that we need to worry about when dealing with the higher dimensional problems that we're going to be discussing for what we've been working on related to surfaces of this form. Okay, so if we have some function that is given to us as z equals f of xy, okay, one of the things that we may do is parameterize the surface. Okay, so in this picture, what I'm imagining is that we have our xyz axis, okay, and there is some surface that we have that is defined, okay, and the way that this picture is drawn right now, the coordinates that we're looking at correspond to movement in the xy plane, okay, so we would choose a point in the xy plane and then imagine where that point sits up here on the surface, this being f of xy, right? Okay. But there are going to be situations where it's more useful for us instead to think about the coordinates, I'll draw it over here, that are local to the surface itself, where I will have a u-axis and a v-axis. We'll do s and t on the surface, okay? And the s and t here are parameters specific to the surface itself. The analog being a parameter t with respect to this surface as opposed to, I switched my colors, I didn't mean to do that. This, right? X is a variable of the coordinate system, and we can have instead a parameter that exists on the curve. The one that we would choose would be arc length, for instance, right? But there's a difference here. So what this becomes is a parameterized surface so that x and y both depend upon the variables s and t, to where I get a position here, and s and t now become the true independent variables. Okay, and x and y are going to be called intermediate variables that describe what's going on here. Okay, now ultimately, we're going to need to answer the question of what does this look like if I try to differentiate with respect to s or t? All right, we'll build up to that. So we're going to start off with case 1 of our chain rule. We're going to have our surface here. And all of our stuff is differentiable and everything. I'm not going to write that a bunch of times. But we're going to assume that both x and y are parameterized with respect to a single variable, t. Okay? In this case, the chain rule has the following form. dz dt, and those are regular d's, is going to be equal to the partial derivative of f with respect to x times the derivative of x with respect to t. Okay? The way that you know if you're supposed to write the partial derivative symbol or a regular d has to do with how many independent variables the function that you're differentiating has. If the function has a single independent variable, then you use a d. If it has multiple independent variables, then you use the partial derivative symbol. Okay, now this is the derivative with respect to x, but ultimately both x and y depend on t, right? So I'm going to get two components to this, where the second component is the partial derivative of f with respect to y times dy dt. All right. Now, we can go through and prove this formula holds, okay? And the way that we would do that is to take a look at the definition of differentiability, okay? I'm not going to go into all the details here, but I want to describe sort of the structure of this. We've seen this definition before when we were talking about differentials, okay? And we have here these epsilon components that show what happens for the change in x and the change in y. Okay, we want this to go to 0, of course. And when we have the expression here for case 1, we get the expression that I just wrote down. And what happens is we set up the differential expression, and we can see through some pretty easily verifiable facts that it has to be the case that both of those limits are 0. Because they are, everything works out when we start breaking things into individual definitions of the derivative using limits. The limit as h approaches 0 of f of x plus h minus f of x over h expanded to the higher dimensional case. Everything works the way that we want it to, and it reduces to this simple formula here. Okay, so the good news is we don't have to do anything crazy in order to make this work out. Okay, there's some definition twiddling that we'll leave aside. A lot of that information is available in the online notes if you want to take a look at that in more detail. Well, let's do an example here. So we'll take z equals x squared y plus 3xy to the fourth power. Okay. And we have x equals sine 2t and y equals cosine t. And what we want to do is find the derivative of z with respect to t. Okay. Now, we look to the chain rule here. And so dz dt is equal to the derivative of f with respect to x. So this is going to be 2xy plus 3y to the fourth power, right? This is all in parentheses, okay? And then we take the derivative of x, with respect to t. This is going to give us 2 cosine 2t. And then we add to this the derivative of f with respect to y, which is x squared plus 12xy cubed. And the derivative of cosine with respect to t is negative sine t. Make sense? Okay. The next step now would be if we wanted to set everything up for us to plug stuff in. Okay. If I have some point that I would want to evaluate this at, okay, say we want to evaluate this at t equals 0, then when t is equal to 0, x is equal to 0, y is equal to 1, according to our parameter functions here. And so now we write dz dt. This notation here means evaluated at t equals 0. Okay. There's not a, in calculus 1, we could get away with just writing parentheses and stuff and putting like the number 0 in an appropriate place. Here, because we're going to be evaluating multiple values at once, it's going to be more convenient for us to use this style of notation. So we'll see this fairly commonly. All right, so we're going to plug in our values here. We get a 0 and then plus 3. And then we're plugging t equals 0 here, so this is going to be 2. And then we add to this 0 plus 0, and then sine of 0 is 0. So the answer is 6. Okay. Now, if we really wanted to test to verify the veracity of this formula in this case, the true test would be to replace all of the x's and y's with their parameter functions, differentiate this thing, and then verify that we get the same answer. We should both get the same derivative formula if I plugged in x and y here, and also be able to reproduce this result. Right? That is a lot of product rule and quotient, or product rule and chain rule to be doing. Okay, I'm not going to do that, but it should be true. Okay, so if you want to make a small test of your differentiation skills, perhaps take the derivative of this, plug in t equals 0, and see if you get 6. You should. Okay. All right. Let's look at now case 2. For case 2, we have the situation that I proposed earlier, where our functions x and y are intermediate variables, and the true independent variables are the parameters s and t. Okay, so s and t are going to be what we want to be able to ultimately differentiate with respect to. Also, I want to note, just so it's said, I think this was covered in Calc 2, but I want to remind everyone, whenever you're using letters for defining parameters and things, they always go in alphabetical order. Okay? Which is why, for instance, when you're talking about polar coordinates, you always write r theta, because theta starts with a T and it becomes in the alphabet after r. Okay. All right. So we need to be able to differentiate this expression with respect to s and t. Now, here we get the partial derivative of z with respect to s, because z ultimately depends on 2 different independent variables as opposed to 1 like it did in the previous case. And so we're going to get 2 terms, or 2 different expressions here. We're going to have partial z partial s is equal to partial f partial x, and then partial x partial s, because x also ultimately depends on more than 1 independent variable. And then we add to this partial f partial y partial s, and then the derivative with respect to t is equal to partial f partial x partial t plus partial f partial y partial t. Make sense? Okay. Now, the textbook has a tendency to use Leibniz notation for all of these types of expressions. It's possible to think about this in another way. For instance, you could say that you want to take the partial derivative of z with respect to s, and then I guess write xy here. Okay. And then through the chain rule, what you would have is f partial x st times x partial s of st. Okay, sorry, this should probably say xy. Okay. This just isn't as clean. There's more things to keep track of. There's ambiguity about which variables we should be writing here and here. Okay, which is why Leibniz notation tends to be the choice in these more confusing situations. Okay, so My general preference is to use Newtonian notation when it's convenient to do so. This is a case where it's not convenient to think about it that way. All right, let's do another example. We have e to the x sine y, and our parameter functions are x equals st squared and y equals s squared t. All right, and what we want to do is we want to find our derivatives. So partial z, partial s is going to be given by the partial derivative of this expression with respect to x. So it's just going to be e to the x sine y. Okay, and then the derivative of this with respect to s, so t squared, and then we add to it the derivative of this with respect to y, so we get e to the x cosine y, and then the derivative of y with respect to s, so we get 2st. If we do the step that we skipped in the previous example and plug everything in, plug in our component functions, what we're going to get is t squared e to the st squared sine s squared t plus 2st e to the st squared cosine s squared t. Make sense? All right. So again, none of this is difficult. It's just a matter of having a lot of note taking to do, right? There are a lot of moving pieces, a lot of things to keep straight, a lot of opportunities to make copy errors or algebra mistakes if you are not someone who is very comfortable with doing a lot of differentiation. Okay. One of the things that I'm practiced at being able to do in my mind's eye is I see stuff like this, and when the variables don't match, my brain just starts tagging stuff. Okay. To me, it's almost as if I see all of these things in different colors. All right. Um, Products and compositions of functions are a thing that I have trained myself to be able to look at and be able to recognize instantly. Okay. Now, this is not something that is a special ability of mine or anything. It was just earned through practice. Okay. Now, I've taught calculus a few times. Okay. So I've had an abnormal amount of practice. All right. But when I was in your position as a student, I had made quite a bit of progress in that already. Okay. Um, the thing that's changed that I didn't know how to do as a student is that now I can explain to people how to figure this stuff out. And nobody was using colored chalk or computer stuff when I was learning how to do this. But it's important to be able to see these things all as separate pieces and organize them in a way that's helpful. Okay. The other thing is knowing when it's appropriate to do the product rule or not do the product rule or whatever. All right. Um, please practice these things because just due to the nature of how the problems work in this class, there's just going to be more things to write down. Okay. And being able to organize in your brain these ideas without making mistakes or copy errors is going to be something that's helpful and a necessary skill in the situations in which I have to evaluate you, like on exams and things, right? Okay. So the next bit of this is more more esoteric looking. We have the general case. Okay. So use a function with respect to a bunch of variables x1 through xn, and each xj is itself differentiable we'll say m variables, t1, t2, all the way up to tm. Okay. Then, when I talk about the partial derivative of u with respect to the ith t, this is going to be equal to the partial derivative of u with respect to x1, and then partial x1 partial ti plus partial u partial x2 times partial x2 partial ti, all the way up to the last one. Okay, so what this says to us is that what we've learned works for a function of any number of independent variables. Okay, it just matters. Um, the only difference is note keeping. Okay, so here I have a function u that's made up of a bunch of variables. Okay, and each of those xj's is itself made up of a bunch of independent variables. Okay, we give these things indices as opposed to giving them separate letters in this case because there's too many things to keep track of. Okay, these are to just count. All right, but we can write down what it would mean to take the derivative with respect to one of these ultimate independent variable tj's by just stacking everything up. Okay, so if we wanted to do an example of one like this, we could say something like w is equal to a function f, sorry, We'll write it like this. Okay, so we have a f, and f is a function of w, x, y, z. This is an example. All right, and w, x, y, and z are all functions of s and t. All right, so if we want to figure out what the derivative of f with respect to s is, we apply the theorem. Okay, so we have partial w, sorry, I guess I have to give this a letter, sorry. I'll call this u. So partial u, partial s is equal to partial f, partial w, times partial w, partial s, plus partial f, partial x, partial x, partial s, plus partial f, partial y, times partial y, partial s, plus partial f, partial z, times partial z, partial s. Okay. And then if we did it with respect to t, it would look very similar, right? So it all works fine. I'm double checking something to make sure that I don't miss a term. Okay. All right. I think we're okay. All right. Now, there's one last aspect to what we want to talk about here, and that is the idea of implicit differentiation. Okay. Now, implicit differentiation was an idea that I'm sure in your previous calculus experience seemed like it was just kind of tacked on in a way that maybe wasn't super helpful. Okay. But here we have a little bit better mechanism to be able to talk about what it is and why it's important. Okay, so if we have some surface that is defined by z equals f of x, y, okay? Let's think about a level set for z equals k, all right? Now, if we set this up this way, then what happens is we can think about this expression as being one where y is now implicitly a function of x. Okay? Now, what I'm going to do for simplicity's sake is we'll call this capital F of x instead, so that it just has a name other than y, so that our formulas look right. This was the adjustment that I had to make to the previous example. Okay, so now, if I take the partial derivative of z with respect to x, then we get partial f partial x here, and then dx dx, because we've reduced to case 1 where there's only one independent variable. Okay, and then we add to this partial f partial y, and then dy dx. And this has to equal 0 because on the right-hand side, the derivative of constants equals 0. Okay. Now, this gives us a nice expression, and if the partial derivative of f with respect to y is non-zero, we can say something interesting about this result. Okay? We have a theorem that has to do with implicit differentiation. Okay? So we have our expression z equals f of x, y. Okay? This is differentiable, and a more precise statement of the theorem is in the online notes, but I'll copy a little bit of information here. On a disk. Okay, so it's on a disk containing a point AB. And the partial derivative with respect to x and the partial derivative with respect to y are continuous. And the partial derivative that we care about here is non-zero on the disk. Okay? Under these conditions, the level set given to us by f of x, y equals k implicitly defines y equals capital F of x so that we have the expression given here at the point AB, and the function has the following property. Partial f, partial x, partial f, partial y. So it looks like that. Okay, so this expression comes from our previous work here. This is 1, and we rearrange and solve for dy dx, which is why we need this to not be 0, because we need to be able to divide by it. Okay. Now, it turns out that this works if we have any number of independent variables or whatever. So we can always, assuming that things are smooth enough, be able to cough up an implicit function by slightly manipulating how we track the indices in accordance with our previous work in the section. Which for us in here, probably not very commonly used result, but when you're trying to prove other theorems about things, having a theorem that guarantees a particular expression of a function is very, very powerful. Okay, so this is the implicit function theorem is something that you will see and use more of were you to pursue classes beyond this. Perhaps looking at a class that is titled Advanced Calculus. Sounds fun, right? Advanced Calculus is where you actually learn calculus. I say that facetiously. It is the class where you go back through and prove the theorems. Okay. With the goal of eventually figuring out that we don't know enough about how integration works to actually be able to do more challenging math. So then you have to take another class called real analysis or measure theory, where you learn the integration, how integration is really done. And then after that, we can do stuff, which might sound fun, might sound not fun. I understand people have differing opinions about these things. Anyway, so let's talk briefly about the next section so that we get a little bit of a head start on our forthcoming class. So this is a brief preview of section 14.6. All right. I'll explain an idea here. It's important for us to understand, and then we'll hit the punchline during next lecture and learn about a very, very powerful and important tool. Okay, so we spent some time a couple lectures ago talking about stuff that happens on a surface. Okay, pretend that that's a paraboloid or something. Okay, and when we were looking at this paraboloid, one of the things that we examined was, draw this next one a different color, cross sections of this surface. Okay, and we talked about the idea of partial derivatives associated with these directions, right? So I had a plane that I cut through that's parallel to the y-axis, right? And that plane generated that level curve on the surface. And I did the same thing in the x direction. I'm not an artist, I apologize. Okay. But we have these cutting planes, right? We did this example in class. Okay, with a 3D picture drawer that's much better at doing this than me. Anyway, we talked about how ultimately what this did was allowed us to talk about the tangent plane, right, to this surface, and we got a lot of nice things. Okay. There's one massive problem with this, though, right? We're talking about derivatives. We're talking about a process that is defined using limits, right? A derivative is defined as the limit of a difference quotient. Okay. But what did we find out about limits when we talked about limits with regard to multivariate functions? When we're dealing with limits, we can travel on many different directions as opposed to just a couple of them, right? But you all sort of allowed me to railroad you into thinking that it was okay for us to just worry about the directions that have to do with x and have to do with y. Okay? Well, it turns out that we can actually take the derivative with respect to any direction we please, not just limited to those cardinal directions given to us by the coordinate system. Okay? Now, we hope that we don't always have this problem of there being an infinite amount of things for us to worry about. Okay? But we have to do the work necessary to talk about how these things go together, and there might be a particular direction that is helpful to us for particular types of problems. Okay? So next section, what we're going to do is we're going to explore this. We're going to clean up the issue of, is it okay for us just to use partial derivatives all the time? Okay? Or and if it is, what other meaningful things can we say about different directions that we're traveling along the surface from the perspective of differentiation? Okay, so we'll do that. I'll see everybody next time. Have a good one.